Swayam Prabha. Digital India. Educated India.
Okay, I think all of you are able to immediately recognize that it is this resistive divider 7 kilo ohm divided by 7 plus 3 kilo ohms times 10 volts. So it is 7 volts. That is the right answer. Okay. So again, there are some complaints that audio is not okay, but it seems that many other people are able to hear. So the problem may be with your setup. You please try it again. Okay. So now the next thing is, what is the value of RTH? What is the value of RTH? Looking into these terminals, again what you should do is you should take the independent voltage source in this circuit, make it 0 and find the resistance looking back into the circuit. Okay. So I have to make this 0 volts or a short circuit, and I have to look at the resistance here. Again, the answer is very simple. This is a short circuit, and you will be able to easily see that the 3 kilo ohm and 7 kilo ohm are in parallel. So the answer is 2.1 kilo ohm. Again, I got some answers like 2.1 and so on. Please don't do this. Always specify the units for any quantity that has dimensions. Okay. Now somebody said 7K parallel 3K. That is correct. So I was looking for the numerical value. Okay. So what it means is that this entire circuit can be replaced by a 7 volt voltage source in series with a 2.1 kilo ohm resistance. Okay. Is this part clear? So now let me make the circuit more complicated. I will add a 10 milliamp current source as shown in red. Okay. So now we want to find now, of course, according to Thevenin's theorem, at 1 prime. Oh, by the way, I should have marked the terminals here. This is 1 and 1 prime. At 1 prime, I can represent this new circuit also with a single voltage source and a resistance. Okay. Now my first question is, what will be the value of the resistance in this new circuit? What is the value of RTH? Again, as many of you are able to recognize, it's exactly the same, because when you null the voltage and the current source, you short circuit this and you open circuit the current source, you are left with exactly what you had before. So the value of RTH doesn't change at all. Okay. Now what will be the value of VTH? The Thevenin voltage source, what is the value going to be? What will be the value of the VTH, voltage source VTH? With the new, with the current source added, okay, what is the value of VTH? So we already see there are many ways of doing it. You can redo the circuit analysis with the voltage and the current source together. You can also use superposition here to calculate VTH as well, because after all it's a linear circuit with independent sources. And superposition means you have to find the voltage VTH due to 10 volts and the voltage VTH due to the 10 milliamp current source. The voltage due to 10 volts you have already found previously, okay? So the only thing you have to do is to find the voltage due to the 10 milliamp current source and add it to the voltage due to the 10 volt voltage source, okay? So the question is about the VTH value with this new circuit which has the 10 volt voltage source, 10 milliamp current source and the two resistors, okay? Now also given some choices. So please do the calculation and let me know what the voltage value VTH is. Can either indicate it on the pole or just give me the value. Okay, I think again many of you are able to do it correctly, although one person said 0 volts. I am not sure why that's the case. So let me do it and show it, although this also is quite simple. I will do this with superposition, which means that first I will set the 10 milliamp source to 0, which is an open circuit, and then I will set the 10 volt source to 0, which is a short circuit. Okay. Now this one we have already done before, so I am simply going to write down the answer. So the answer here is 7 volts, and this other one, you should be able to see that this 3 kilo ohm and 7 kilo ohm are in parallel, and they are in parallel across this current source. Okay. So we have an equivalent picture like this. This is the 10 milliamp current source, and this is 3 kilo ohm and 7 kilo ohm in parallel, which is 2.1 kilo ohm. Okay. Now, by the way, this is 1 and 1 prime. So the voltage across this from 1 to 1 prime, that is with V being 1 being positive, is minus 10 milliamps times 2.1 kilo ohms because of this polarity of the 10 milliamp current source. So 10 milliamp is being drawn like this. So this voltage is minus 10 milliamp times 2.1 kilo ohm, which is minus 21 volts. Okay. So again, if you have got some different answers, please look at this and then figure out where you have gone wrong. So the total voltage is the sum of this due to 10 volt source and this due to the 10 milliamp source. So clearly minus 21 plus 7 is minus 14 volts, and this is the correct answer. Okay. So with the current source added, what we have is minus 21 volts and minus 14 volts and 2.1 kilo ohms in series. Okay, 1 prime. So what I tried to demonstrate is that even if you make the circuit more complicated, you can represent it equivalently. Okay. Now this will be the equivalent circuit regardless of what you connect to 1 and 1 prime. Okay. This hopefully you understood this point, that I connected some Ix here, and that Ix can be either a current source or a representation for any kind of load. So whatever you connect between 1 and 1 prime, that doesn't matter. This part, what we are replacing is this part here, that can be represented by this minus 14 volts and 2.1 kilo ohms in series. In fact, what you connect to this can be non-linear. The part that we are converting to Thevenin equivalent, that has to have only linear elements and independent voltage and current sources. Okay. Now there is a question about the polarity of the current source. I think you got the answer right anyway. So what I am saying is that if you have a current like this and then you have a resistance, okay, so the voltage measured with this polarity will be minus I times R. Okay, so if the current was flowing like that, if the current I is flowing like that, the voltage in this polarity will be IR. Okay, now if the current is in the opposite direction, which it is, if I is like that, it will be minus IR. That's all I said. Okay, is that clear? Okay, so now just for we'll take it just a small step further. Okay, let me add another resistance like this, which is 1.9 kilo ohms. Okay, I'll take some value, and again at 1 prime I have to find VTH and RTH. Okay, now please tell me, how will VTH and RTH change? For this new circuit with this 1.9 kilo ohm resistance, what will be the value of VTH? Previously when we didn't have this, this was the value of VTH. Okay, so what is the value of VTH when we have that 1.9 kilo ohms? So I think many of you recognize that VTH will be the same, because when this is open circuited, that's how you find VTH. This 1.9 kilo ohm is floating and no current is flowing through it. So whatever voltage appears here will be the same as what appears there. Okay. So this is a special case with the way I have connected this 1.9 kilo ohms. But when I open circuit this, no current is flowing through that. So whether you have this 1.9 kilo ohm or not, you will get the same voltage. Okay, what will be the value of RTH? So again, this is simple, because we have the 3 kilo ohm and 7 kilo ohm in series, okay, and this 1.9 kilo ohm like that. So we know that looking here between these terminals we had 2.1 kilo ohms, and this 1.9 kilo ohm is simply in series with that. So looking this way it is 4 kilo ohm, that is 2.1 plus 1.9, okay. So the equivalent circuit for this including that would be minus 14 volts and 4 kilo ohms, okay. So this is just to illustrate the point that you can make the circuits more complicated, but the representation can remain exactly the same, and you can find the representation, okay. Now this circuit is still too simple. Even if you had 100 resistors and then control sources and so on, you can still find the Thevenin equivalent circuit, okay. So any questions so far on any of these calculations or proof of Thevenin's theorem? Okay, so that seems pretty clear. Now, there is another theorem which I will not prove. You can try to prove it yourself by following analogous methods, and if you get stuck somewhere you can ask me later. So instead of using a voltage source and a resistance in series, okay, any network of the same type, any network with linear elements and independent sources can be represented by a current source IN and a resistance Rn in parallel, okay. So instead of a voltage source VTH and a resistance RTH in series, we can represent the same by a current source IN and a resistance Rn in parallel, okay. So now it turns out that this IN is now what is known as the short circuit current, and this Rn is what is known as the Norton resistance, okay. So we have the short circuit current and the Norton resistance. Now what is the short circuit current? The short circuit current is, you take this terminals 1 1 prime, short circuit it and measure the current, okay. So you short circuit this one and measure the current flowing from 1 to 1 prime, that is the short circuit current IN. Okay, and Rn is the same as the resistance looking into this circuit with all the independent sources nulled, which will be the same as RTH. Okay, so the Norton equivalent, the resistance in the Norton equivalent circuit and the Thevenin equivalent circuit will be exactly the same, because they are nothing but the resistance looking into the circuit N with all the independent sources set to 0. And this IM is the short circuit current, that is when you short circuit 1 prime, you will have a current IN, and this VTH is the open circuit voltage, that is if you have an open circuit across 1 then the voltage that appears at 1 is VTH. Okay. Now this IN is of course related to VTH in a very simple way, and a very easy way to see that is, first of all, this is the Norton equivalent circuit of this, and this is the Thevenin equivalent circuit of the same circuit. So clearly these two also have to be equivalent to each other. And if you look at the open circuit voltage between 1 prime, what we have is VTH itself, because by definition that's the open circuit voltage, and here also you see that no current flows through RTH. Now in this case, if you open circuit 1 prime, all of this IN will flow into Rn, and the voltage that appears is IN times Rn. Okay, and these two have to be equal to each other. Okay, so IN times Rn equals VTH, or IN times RTH equals VTH, and Rn and RTH are the same thing. Okay, so I hope this is clear as well. So instead of using a voltage source and resistance in series, you can also use a current source and resistance in parallel as an equivalent to any two-terminal circuit which has independent sources and linear elements. Okay, and this idea of using a current source and resistance in parallel is known as Norton's theorem. Just for completeness, let me write out the statement. RTH and Rn are the same, and IN is short circuit current between the two terminals. When you short circuit it, that's the current that flows there. Okay, so again I hope this is clear. So very quickly we will evaluate this. What would be the Norton equivalent? This has to be represented by a current source IN and a resistance Rn in parallel. What will be the value of Rn in this case? What is the value of Rn? So clearly it's the same as RTH we already calculated. So this is 2.1 kilo ohms, And what's the value of Im? Then again, all of you are able to recognize that it is 10 by 3 milliamps or 3.33 milliamps. You can either get it from the previously calculated Thevenin equivalent circuit, that is, we had 7 volts and 2.1 kilo ohms, and we know that Im times RTH equals VTH. From this you can calculate, or even in this case, looking at the circuit, if you short circuit this, what happens is that we have this 10 volts and 3 kilo ohms and a circuit like this. No current flows through 7 kilo ohms because it has 0 volts across it, and the current that flows this way is 10 volts divided by 3 kilo ohms or 3.33 milliamperes. Okay, so now you can also try it with all these other things added. When I added the 10 milliamp, etc. Okay, you can figure out what happens. Okay, so that's the story with Norton's theorem, and you can prove it in exactly the same way that we proved Thevenin's theorem. To prove Thevenin's theorem, what we did was we used the current source here and then use superposition in some way. Now instead of a current source, you can use a voltage source. Like any load can be substituted either by a voltage or a current source. So let's say you substitute with a voltage source here, and then you apply superposition, and then you can try proving Norton's theorem. Okay.